Thanks. Okay, let's start. So the plan for, unfortunately, the last lecture, the last session of this course is to finish off this, some of this, I would call this advanced part of the microarchitecture related to pipelining issues. These are, these, I would say, gives you some sort of flavor how these advanced stuff that obviously you're not going to go into much detail looks like when you take more advanced computer architecture courses. So somehow you see some flavor of this. But before we start, do you have any question that I can answer now? Okay, so if you remember, we had an example that we analyzed, and we drive the speed up that we get. And again, the last column here is the speed up comparing with the execution, the original baseline execution of the single cycle. So when we discuss a speed up, you should always think and ask yourself, what would be the baseline? Here, the baseline that we compare against, or we calculate this speed up, is single cycle. So you can do the calculation yourself and derive these numbers easily. And we find out that the pipeline microarchitecture that we discussed, even though it has some sophisticated implementation, some details, some hardware that we added, and like some resources like multiple pipelines, would not deliver the performance that we expected. Obviously, like you can think about some variations, some better implementation of these ideas, and also a speed up is one of the aspects. The other aspect that we have always discussed is the other dimension of performance, which would be the cost, and also something that we did not explicitly mention here is the energy consumption. That you can think about it as either an objective that you want to minimize, or as a constraint, because one very important aspect of chips that architect design is these power constraints. So if you design a very sophisticated chips that basically deliver a very good speed up, very good performance in terms of execution time, it may turn out to be unstable, meaning that as soon as you run some programs on it, it would basically, it wouldn't work after some time. It basically melt down after like huge energy that it consume, because you know that the higher energy means that basically the heat would increase, and the whole system may not be really stable. If the heat increase, at some point, like you see higher error rate in the chips, different part of the chips, but also after certain temperature, it will melt down, and you will lose the chips that you design. So, like again, this slide only talking about the speed up, but there are some other dimension that you are aware of it. Okay, some aspect that you also need to ask and think about it, because some of these issues and also the solution that we have discussed could be handled, as last time we discussed, at the hardware level or at the software level. Hardware level, meaning that we need to add some logic gates to the hardware. Most of the solution that we discussed, actually all the solution that we discussed, was implemented at the hardware level. You remember, like last this in particular, I'm sure you remember, data forwarding. For example, we needed to add some data paths and some muxes, and for early branch resolution, we added this gate to check the equality. So these are obviously, you see that were implemented at the hardware level, but it doesn't mean that it has to be implemented at the hardware level. Some of these could be handled at the software level, meaning that some of these dependencies could be handled, could be first of all detected by the compiler, because compiler has a full knowledge about the instruction. Actually, the instruction were in the first place generated by the compiler. If you think about the compiler, read the high-level program that you wrote in C++, in Java, in Python, right? We compile it to assembly. So the compiler knows everything about these instructions, and with enough knowledge, because compiler generated this instruction in the first place, knows the dependencies between these instructions, right? So knows the, and we have, you already know that we have like data dependencies, control dependencies, so we have different type of dependencies, right? So compiler has a full knowledge, so these can be handled at the, these interlocking, these interdependency could be handled, detected and handled at the software level. And there are some nuances that you can think about it. Like, for example, if the compiler need to take care of, say, handling this dependency. For example, you remember we discussed about these bubbles that needs to be inserted between different instructions. So we handle this, basically, we make sure that we produce the value of a register first before like some other instruction that needs to read from this register. So we need to insert some bubbles. We had some examples. Compiler can do that, obviously, for example, by inserting no-op instruction. And we have no-op instruction as a defined instruction at the ISA. So this is this no-op is part of the ISA. So compiler can insert this valid instruction, right? And like, it is important to think about it. Like, you have one program, because it is always important to ask yourself one very specific, at the same time, very important question. Let me make it clear for you what I'm talking about. Okay, so one thing that you need to remember, when we have a program, right? We have a program, let's call it P1. We want to make some changes, obviously. When we say that we want to insert some bubble, some no-op operation, this means that we want to change this to another program, right? And this change, who takes care of this change? Compiler, okay? But one thing is very important, is that we don't want to change the semantic of the program, because otherwise P2 would be a different program than P1, is like has different semantic, okay? We want to preserve the semantic of the program. We want to preserve this semantic of the program. So if you want to think about it, if you want to represent it, P1 should be the same in terms of semantic than P2. And when we have this relation, this means that at the semantic level, at the whatever we want to do, and by semantic I mean if we want P1 to add the values of two arrays, right? We should get the same result after we execute P1 and also after we execute P2. This could be like different instruction, but the produced value, meaning that the semantic of this program should be exactly the same. You don't want to change the semantic. And by inserting no-op, we already know that we would preserve the semantic of the program. This is one of the program variation operation that we do, or the compiler does, that preserve the semantic, but this would help in order to handle this dependency between instructions by inserting some bubbles. You can think about it as a bubble. So this basically delays the execution of some stages in your pipeline. So make sure that it makes sure that the pipeline would execute the program, and as a result, it automatically handles these interdependencies. So meaning that if you have some instruction, you may want to, add no-op, right? Right, and this would be the same as like the original program that you have written. So this is one of the operation, and like this is one of the changes in program that would preserve the semantic, okay? Because this is important to understand. So this in the dependency or interlocking solution can be well handled by the software too, not necessarily at the hardware level. Okay. And when we have two various solutions for doing something, obviously there would be again like some disadvantages and advantages as well that we should understand. And one way of thinking about it is to think about the performance equation. So for example, in the software, if we insert no-op, obviously we change the basically number of instructions. No-op is again an instruction that we inserted to the pipeline, to the program. So we vary the number of instruction. And you know that in performance equation that you should already know, we had 3 components, one of which was number of instruction. and the software interlocking basically changes that. So obviously it varies the execution time, but the hardware solution didn't change any instruction. It didn't add the no-op instruction. It handles it differently, but the CPI, the clock time, as a result that we discussed, by adding this hardware, if you remember, I asked a question and Noah correctly answered it, that it may change the basically one of these component of the performance, which was related to the CPI, right? So as a result, the performance, the execution time may change or may not. So both of these changes may result in the same execution, may not, but obviously has some performance consequences and obviously has some cost that we need to pay. So meaning that the software may be easier because we don't need to add hardware pieces. So it would result in a lower cost for the hardware, but it means that like the compiler should be more sophisticated and so on. So trade-off again. Is it clear for you? So these are some, again, advanced topics that I better discuss, and you better have a flavor of these advanced topics in microarchitecture and computer architecture overall. There is also one other important differences between this software and hardware level solution, which you need to, most of you, I'm sure you understand this and you can guess what is this difference is that. When we basically ask compiler to handle this, or when we assign the role of this scheduling or interlocking, handling this interdependency to the compiler, has some disadvantage with respect to the hardware. And one important disadvantage that the compiler has, even though it, but also has some advantage, right? So we discussed that this instruction would be produced by the compiler in the first place. But compiler doesn't know one thing, one very important thing, is that when we are executing the program on the hardware, at each time, the hardware knows exactly the architectural state of the program, knows basically the current state of the program at execution time. But compiler only has static knowledge about the program, meaning that it knows the list of instructions, the dependency between instructions, but it doesn't know, okay, at execution time, for this specific workload, if I execute it, like what are the architectural state at each time point. So it doesn't have the notion of time, it doesn't have the notion of a state. It can construct some knowledge based on this static information of the program, these instructions and dependencies between these instructions, right? So it can create some, ASD type of data structure, meaning that the workflow of the instructions, right, from the static point of view, but not dynamic point of view. So that's also one aspect of these differences that you can think about it. That is important to understand. And this again would vary the performance, as a result would change the complexity because hardware has this advantage of knowing the current architectural state and so on, and obviously has the advantage, would result in a different power consumption, reliability, and so on. So it has influences on all non-functional aspects of the system, and all of these things, metrics that you see here are again, I'm sure you have heard about non-functional properties, right? When we say property, how many of you have heard about functional, non-functional properties? Can you confirm whether you have heard about this term? Anybody can confirm whether you have heard about these terms in any of the previous courses that you have taken? If you have not, please maybe mention in the chat so I can see. And if you have, in what context?
I've heard them a little bit, not very much though. It was in a class I took on electrical modeling and simulation, circuit modeling.
Mm-hmm. So these terms, if you have not, maybe in some other courses you will, like some software engineering or system courses, you will hear at some point some programming courses, especially. So when we say functional, again, this is related to the function that this program is supposed to do. Each program is supposed to implement one or multiple functions. So when we say functional properties, means that whether this program that we wrote, implement, or execute the function that's supposed to implement or not. Okay? So this is the functional aspect. Non-functional is the scenario when we say that the system would execute the functions supposed to do, but have various way of execution, meaning that the execution time of them would vary, meaning that we might have program 1 and program 2 implementing the same function, but having the same different performance, different complexity, different power consumption, different reliability. So all of these aspects are non-functional, meaning that these two programs, P1 and P2, are the same in terms of function. So they have the same functional properties, but would vary in terms of non-functional aspect. All of these things, this list that you see, these are non-functional properties of the system. So whatever is not functional, you call it non-functional properties. So again, the compiler can order the instructions, a hardware execute them in that order. These are obviously this is obvious for you, and we discussed, like, in dynamic scheduling, hardware basically has this advantage of knowing this architectural state and the latency of each instruction, but the compiler obviously doesn't have any clue how long an instruction would take when executed, right? So this is, for example, one specific piece of information where the compiler doesn't know, okay, like this instruction that we have in the program, how long does it take? And based on this, like we may want to have different scheduling policy, right? You will hear about this scheduling in some other courses as well, like operating system, some of you, or in some other also mathematical courses as well. So dynamic scheduling, because we have several different scheduling policy, strategy, paradigm, whatever you want to call it. So knowing the latency of each instruction, for example, maybe like you have a scheduler, and scheduling means that you have one resource, you want to order this, which one goes and be processed first, right? You want to make an order. If you don't know the latency of these things you want to execute on this node, on this resource, maybe you don't have much preference in what order you want to execute. Maybe the best thing that you can say based on the order that these were generated, right? But if you know about the latency of each instruction, maybe it's better to execute, for example, the shortest one first. This is one strategy, shortest one first. Another strategy, the longest one first, right? Another strategy, in a random way. So you have many ways of putting tasks into resource that you want to go and execute. So knowing more about the state of the program would give you the flexibility of reordering things in the way that would improve performance. And again, you might ask, hey, don't we know that like we should execute the instruction sequentially? Yes, that's at the programmer perspective. That's one property that we want to preserve. But we discussed that at the microarchitecture, if we could hide things, if we could reorder things, as long as the architectural state would show to the program that we are executing things in order based on the order in which these instructions are located in memory, then we are fine. We can mess with things with the order of execution and so on, as long as we don't reveal to the programmer, because we want to preserve this property. This is the important property that are specified in one human machine. Okay, so these are important to understand because it has some implication, and it has very important association to these advanced ideas like out of order execution, for example, and some other advanced ideas in microarchitecture, which obviously we are not going to cover. But one takeaway that I would like you to understand is to know these differences, at least this trade-off between software handled and hardware handled, and what would it mean, why there are some differences in terms of implementation, and the benefit or disadvantages that you can think about it. And there are also some work or approaches that also can help the compiler maybe to gain advantage of whatever like hardware knows. For example, you could profile the program, you could construct a belief or a model. How long does each instruction would take if it gets executed on this hardware, right? So profiling is one way to construct this knowledge and help the compiler to know more about this information, and this would obviously help the compiler to schedule things in a more informative way. So it doesn't mean that there's no way that this information could be revealed to the compiler. Profiling is one way. Profiling means that you execute a program, right, on multiple different workload, and you construct some statistical model or some non-statistical model to give you an idea, okay, like how long each instruction would take, and some other extra information that would help for doing the scheduling. So this is important. Okay. Right.
A quick question about profiling. Is it very different than building for specific targeted architectures, like very, very specific processors? Like if you want to build, like you can specify in compiler flags, you want to build for a very specific processor. Is that related?
Awesome, awesome. Very good that you mentioned about compiler flags. Yeah, this is very, very relevant. No, so profiling itself is not much, at least in this context, really related that much to the specific microarchitecture, right, or a specific architecture overall, right? The idea is to gain some information about the execution time that might help the compiler to do some task in a more informative, in a more performant way, rather than just relying on the static information that it has, right? So it's independent from the architecture, but you have seen some construct compiler and also like some construct, for example, say in some other high-level programming languages like C++, like feature flag that you can use based on a particular architecture, how you want to, how you want to write your code, right? So you could obviously put some architecture-specific logic in your program if needed. I mean, not all program needed such feature flags that varies depending on the architecture. But for example, say you have a program that you mainly you want this program to be executed on many different machines, right? Say not necessarily one particular microprocessor, but you want to have a portability across many different microprocessor. So obviously you want to have some logic, you want to use some of this feature if this executed on x86 or like AMD or like some other chips. Like what are these specific logic you want to you want your compiler be aware of it. So this feature flag would help the compiler. Again, these are like, if you think about it, these are some static, some clues, some useful information that you want to, some logic you want to provide to help the compiler to compile the program for each particular chips accordingly, to increase the portability. Does it make sense?
Yes, thank you. Sorry for the getting sidetracked.
No, that was a perfect question. Thanks for asking. One thing is that in multi-cycle, is not the case that all instructions take the same amount of time, specifically at the execution stage. Execution is one of the stages, right, of the instruction execution in the pipeline, meaning that maybe you have an add that takes like one cycle, very quick. You have an integer multiplication, which may take like 4 cycles. You have floating point multiplication that takes like 8 cycles, right? So depending on the specific type of instruction, you may have different time, different number of cycles that you want to assign to each instruction, right? And we want to take care of it, right? So the idea is that we can have multiple different functional units to take care of these number of instruction. And as you know, like the construct that we have in multi-cycle would allow us to do so, right? But the question is that what are the challenges when it comes to pipeline execution, whether these can be pipeline or not, and what would happen in independent and dependent scenarios that we need to take care of, because they will have some consequences in terms in these scenarios, whether like we have independent instruction or dependent one, and like when we have like these variability in terms of execution time, specifically at the execution stage, as you are aware of. And like, for example, this is one scenario, one type of program that you see. If we put them, like if we put like, say, like this into the pipeline, you see that like the first one is floating point multiplication, R1 and R2 putting into R4, and then we have add, which takes 1 cycle for execution, in total 4 cycle. The floating point, we require 8 cycles for execution, and we have like you know, the other stages that you are aware of, like decoding, write back stuff, right? So you see this variability for the execution, and as a result, you see this fragmented pipeline. And you can like easily see that there is something wrong here, meaning that if that's the case, because like previously, to remember, where is that? So the other type of pipeline that we see, for example, here, right? So here we obviously assume that each of these, I mean, implicitly, the execution would be equal, right? So you see this, unfragmented pipeline where whatever entered to the pipeline, this one, I mean, forget about dependencies of these, think that these are independent. Whatever instruction entered the pipeline automatically would go out of the pipeline in order, right? So this came first. So as a result, this would go out first, right? You see this. This came second. This would go out of the pipeline second. This would come third, go out of the pipeline third, right? Again, forget about dependencies. But if we have like different execution, different number of cycles for execution or other cycles, other stages too, then this property, we don't get this property, which is which you see obviously here, right? This one came first. Does it go out of the pipeline first? Does it? Obviously not, right? Which one goes first? The second one. And then this one, and then this one, right? And then this one, and then this one, and then this one, and then this one, right? So it completely, would violate the assumption that we had with the von Neumann model, von Neumann machines, which the sequential execution of the program were not preserved, right? Which basically is so let me ask you why this claim is true that the sequential semantic of the von Neumann model were not preserved in this execution, in this pipeline execution. Can you articulate that? Can you give some intuition why that's the case in this scenario? I want you to answer.
We're talking about what's wrong with this type of execution, correct? With the von Neumann architecture respect, basically that point at the bottom that you have.
Yes.
Yeah. So it says it on the slide as well that the it doesn't preserve the sequential instructions that we want from the von Neumann architecture. The von Neumann architecture, we want to execute one instruction all the way through and then do the next one and then do the next one, or at least stage them so that we're doing separate parts in a row. We don't want to have this where the instructions finish executing out of order as well.
That's right. I already mentioned that. Why I'm asking why we get this. I mean, like when exactly things went wrong. When exactly things went wrong, and when this constraint, this property that we have in von Neumann were violated.
Oh, okay. So in this program, it went wrong with that multiply instruction toward the end, where it has a very long execution time, which extends longer than regular instructions would. And because of that, it's going to finish executing and it's going to finish writing after the other instructions would have already finished their processes. That's why. So it ends up shifting everything out of order.
Right, you're getting there. You're getting there definitely. But let me elaborate on that so you fully understand.
Doesn't it?
Yeah, go ahead.
Doesn't it like break whenever there's an execution and an execution in the same cycle. Like that's when it breaks, because the next instruction is executing while it's like the actual instruction is not fetching, but like the multiplication and the addition are being performed at the same time.
That's actually very right. That's actually, I like this, that I myself did not think about it. So basically you are referring to this, right? So like you have
when there's two E's in the same column.
And the same column. That's fantastic. I did not think about it myself. Which is clearly an issue, right, in this pipeline. Very good. I like it, Eric, that you mentioned. But what I was thinking about something else, that somehow we're close to get it right, but I want some explicit when exactly in this pipeline, if you could refer things went wrong. I mean, think about it because like when we have a pipeline, obviously that you can think about this from different perspectives. And I like the way how Eric thought about this, because it clearly shows that he thoughts about like this different perspective, right? So when we have a pipeline, let me go to this. Okay. So when we have a pipeline, right? So we have this thing, then we have like, no, sorry. What is this? Yep. Then we have this thing, right? Whatever. Something like that, right? So when we have a pipeline like this, and actually this is not, again, a correct pipeline, because one thing is violated. Oh, come on. Which is one thing, like, exactly, is that these instructions come to the pipeline sequentially, right? So basically this means that the first stage, right, would be listed sequentially, right? So we don't have this situation, right? This is not the correct pipeline. This means that this entered at the same time of this, which is obviously not the correct way of doing pipelining. So we should be aware of this. All right, but in this scenario, like we discussed that, like after we have this decoding stage, we might have various execution for this. We might have longer execution, right? And then we have write back, and then here, like we have shorter execution, we have write back, and then we have shorter execution, we have write back. We have shorter execution, we have write back, and then like we might have longer execution, and we have write back. Okay, so in pipeline we have like two dimensions. One is the orders of instruction, right? Can think about it as from the column perspective, right? As Eric mentioned, like for example, like how comes these two executions can be aligned, be in the same column?
in the same cycle.
Yeah, in the same cycle, because we have one resource and like we cannot do the same thing at the same time. So this is obviously one way of looking at this, but also one way of looking at this is from row perspective, right? Where so from this perspective, right, where it concerns total different point of view, right? Basically, it concerns the depth of the pipeline, right? So basically, this is what it concerns. These things, this new aspect that we discussed, we might have different execution, different cycle assigned to execution, right? We might have shorter one, we might have like longer ones, right? So it's basically one concern the depth of the pipeline, and one concern the width of the pipeline, right? So these two aspects are important. And this thing that Eric mentioned is very good. What I meant was something else, which is also important. We want to get it right because we claim that this is wrong with the one Newman architecture. And one Newman architecture, we know that we have this property of sequential semantic of the program, which is not obviously preserved, and we want to preserve it. What I ask, like, how do I see this in this pipeline, that the sequential semantic is not preserved? Because obviously they came to the pipeline in a sequential way, but when exactly from the from now, not when exactly from both perspective, both depth and width perspective, things went wrong. Like now I want you to think like in 2 dimensions about this pipeline, that you can, give some intuition or some reasoning why and when exactly things went wrong.
Well, the reason I was saying about the column being occupied with 2 executions is that the ALU is already occupied in that cycle, like doing the previous instruction. So that overloads it in that way. But in terms of instructions, doesn't it, like the previous instruction hasn't finished, and if it's doing something else, like doing something with, let's say, S0, and the next instruction also does something with S0, the fact that the previous instruction has not finished, that the write for S0 occurs, during the execution of the previous one, causes an issue. That's also has to do with S0. I don't believe I'm talking the right way.
No. You're getting there. You're getting there, and you are on the right way, right? So you are referring to the fact that but you're assuming one thing, that there might be some dependencies between these instructions, right? Which might be the case, right? So we are executing something that actually comes, for example, here, like here, you're executing in the second or in the third, that may depend on the first instruction that is actually going to be written like some later time, right?
Yeah.
Right. But you have this implicit assumption that there might be this dependency. Now I'm making it clear that assume that there is no dependencies between these instructions. Assume that this, like second, third, for example, doesn't have any sort of dependencies, or all of these instructions are totally independent. So no interdependencies at all. So the compiler used renaming of these instructions in a way that like there are absolutely no dependencies between these. So we are not worried about that. But and this is important to get it right, things, even though like there is no dependencies, and when there is no dependencies, like we can execute things like in any order, it doesn't matter, right? As long as we execute them. It doesn't really matter, but still, like we want to have this property for some reason, and things actually went wrong in some specific stage. And like you already see that, you already mentioned that, but I want you to make it explicit what a stage and why exactly it went wrong in terms of violating this one Newman property, which is like sequential execution of the instructions.
There was supposed to be a stall, I believe, but there was like, this doesn't indicate that there's a stall, like, because the execution lasts 4 cycles. So like there needs to somehow, the next instruction needs to wait on the previous instruction in some way.
But this stall, again, I'm happy that you are referring to all of this, because these are important, and like discussing this is important for you to, all of you to get it very right. And please listen to this, all of you, right? Yes, but we need a stall in the case where we need, like, say, this guy, the second one or third one may need to in the execution, like maybe they need a value from the first, where really like how can I execute this stuff that like we don't have its value yet, right? So in the execution, after we decoded it, we find out, okay, like we need a value to be in a specific register that is actually were produced in the first one. But again, I'm saying that like in this scenario, since we don't have any interdependency, or since I mentioned there is no dependency, and you can see that like in the slide, if you refer back to it, that actually there is no data dependencies between these. And let's assume that this instruction doesn't have any sort of dependency, so this execution actually can be safely executed in this order. I mean, irrespective of like the concern that you mentioned, Eric, that like this should not be aligned in the same column, because I mean, like we don't have two ALU, right, in MIPS. But again, imagine that like we don't care about this. Imagine that we have multiple ALUs, and somehow we can execute this in this way. Can you again reason more when things went wrong, and when we sure that like this property was violated? When exactly? Yes, Bella.
Okay, so things went wrong in the order we wanted to do all the steps. Since they're not dependent on each other, we could have chose from least to greatest, which would have fixed this. And so we went wrong from the first step because we chose one of the longer steps to process.
That's also fantastic things that you mentioned. Fantastic things that we can definitely do that. We can definitely do this reordering, as Bella mentioned, which is a fantastic idea. And since we have this no dependency things, we know that there is no dependencies. We obviously, in terms of semantics, nothing will go wrong if we reorder thing, and like it makes sense to maybe execute this first and then this too long, right? We can reorder execution, why not? Because we can get a better performance. But we can reorder things as long as we make sure that we have not violated the von Neumann model property, sequential semantic of the program. And so basically, this way of phrasing the question, I mean, I said that we can reorder things as long as we do not violate this property. How we can reorder things if in a way that does not violate this property? So this is like one other way of asking the same question. Like previously, I asked you when exactly things went wrong, when exactly things we lost this property of sequential semantic of the von Neumann model, execution of von Neumann model. And like now I'm asking the same question in some other wording. Like imagine that like you want to reorder this instruction, how you can make sure that like you preserve this property. Do you have any suggestion how we can reorder things that yes, Bella?
Okay, so my suggestion is to try to determine some way to figure out how many executions are in each one, and then go from least to most. And then that way, the shortest one would go first, and it would not violate the von Neumann model.
Yeah, exactly. So basically, what Bella says that maybe like this would come here, and then maybe it looks like, so basically the pipeline we may want to look like this, and then this guy, and then this guy, right? And then maybe this guy, right, which has you know, slightly longer stages, and this longest one, right? Okay, so this makes sense. This reordering totally makes sense, and this is a good idea, right? So this is like F, D, E, W, right? F, D, E, W, and W, W, right? And these are E's. F, D, F, D. These are all E. Okay. This is, I think it's perfect. Like, I agree. But even in this, I violated this property. I violated the von Neumann model. How? So I'm asking how. I mean, this is the right way of ordering, and this requires you to think about this 2-dimension. I mean, you get this perfectly in terms of like if you wanted to maybe get a better performance of reordering this instruction and reordering, you thought like this way, you know, from this perspective. But now I want you to think along 2 dimensions to first get this property right that we want to preserve, and also maybe you're free to reorder in whatever you want to reorder, and this reorder makes sense. But how you can make sure that you get this property right? Because this was the original ordering. How you want to make sure that you do not violate this assumption, even though you are free to in pipeline to reorder things in however you want to do. Let me help you because this is very important, but listen very carefully. Things exactly went wrong. Actually, forget about this very important thing that Eric mentioned, which is true, but like forget about it for a while. Things didn't go wrong from here to here, from here to here, from here to here. Things went wrong at the right stage. Why? Because this is where actually the architectural state of the program was revealed to the programmer. So programmers, we discussed about this, like whatever you reveal to the programmer to the ISA level, right? And this revealing, like we have like multiple components that reveals the architectural state, one of which was like these register files, right? These registers that you have is part of the architectural state of the program. PC, others like were also part of it. You reveal the architecture, you change the architecture state in this stage, in write back stage. But you did not actually until here, until end of execution, you did not really change the architectural state at all. So if you actually like imagine if you do the same way, but if you instead of doing the right, the first one is fine. If you do this right after this one, if you like remove this and put this right back here, do the same, do this right back here, do the same, do this right back here, and do the same, do this right back after this, the previous one, then you are not violating this property at all, because you do not reveal the architectural state to the programmer, right?
Professor, I didn't see when you were drawing there, I didn't see what you were drawing. Really? It's still static on my end.
I had the same issue.
Oh,
Same here.
Oh, sorry. I don't know, sometimes this happens. Let me.
Just to clarify, it's what you were saying had to do with as long as it doesn't matter. Well, not that it doesn't matter, but like as it's a black box, like as long as it functions as any other von Neumann machine, it works fine. Like it doesn't matter how it's pipelined. Like it writes after each instruction writes after the next instruction before the next.
Exactly. So see this now. I believe you see this green stuff, right? So these are what I was writing and you didn't see. Sorry about that. So imagine that we remove this. This first write, fine, right? So imagine that this long guy came to the pipeline first. That's fine. You're right. We do this right. We remove it. We push it to the stage after this one, right? So this cycle right after the first one, right? do the same right after the second one, right? And do this writing of this guy right after the third one, and so on, right? So in this case, after we make this change, if you see, like the architectural state would change at this cycle for the second one, at this cycle for this third one, right? And with this change, you're not violating this property, right? So basically, you did not violate the property until here, until here, until here. Things went wrong at the write back stage when you changed the architectural state, right? In this way of reordering, also, I mean, in this example, this reordering actually, so what happens is that you, what instruction was it? This instruction was actually, you change the architectural state in the first place, but this instruction was the second one. But here, like, you obviously violated this von Neumann, but like, because you needed to communicate the architectural state of this guy first. So this guy was the first one who the programmer should see the result of it, right? Because this was actually the first instruction in the program, right? And you violated that, right? Obviously, you could like reorder things as long as if you move this right, like to a place that you make sure that you write after this last guy. That's fine. You are not violating this this property, this von Neumann, and do the same for the others, right? But this reordering without taking care of, like, when you are writing to or changing the architectural state, this obviously violate the von Neumann. So one important thing that I wanted you to understand is that, like, when things will go wrong, when you violate this property, when exactly you change the architectural state, right? And the architectural state of the program will change, right, in the write back. And this is what I wanted to you to get it. All of you, like, answer it correctly. I mean, explored some very interesting things, aspect of the pipeline, but I want you to fully understand this important aspect of pipeline execution, right? Because this is important concept that we have discussed several times. I'm sure now with this you have much better understanding what I'm saying, and actually this is very important. This basically having this property, I mean, this property of von Neumann model sequential execution is important for some reasons. Let's forget about this. I don't want to go into this detail, but I want you to understand why we want to have basically this property, because to help software debugging, to help debugging of the program, if you change the architecture, say if you violate this property, this is a contract that is specified in the ISA, in the ISA of your chips, right, of your architecture. Otherwise, programmers, there is no way of, like, debugging or handling the exception, because exception could happen. I mean, imagine that like in the first instruction, let me make it super clear for you. Imagine that you are executing this program in this pipeline, and then you have this, right? So you obviously in this pipeline you violated things, right? So you change the architecture state like in like totally different order. But imagine that the first instruction would fail. But previously, like you executed the second, third, and fourth instruction, and also like this guy, and also this guy, you executed all of these other instructions, and this first instruction have failed. And then like programmers' assumption is that, wait a moment, right? Why this architecture, why I'm seeing this, right? So it doesn't have any way to debug the program, because the assumption is that this instruction has failed, meaning that all other next instruction should not have executed yet, and all previous instruction should have executed already, right? Which is important property, right? Imagine that the fail happened in the third instruction, right? So if this third instruction or the second instruction would fail, this imagine add would fail, right? The programmer assumption is that the previous instruction has already executed. But obviously within this pipeline, no, like this instruction has not already executed, like it will be revealed to the programmer like very late on. And this obviously would basically, violation of this property basically make the debugging very difficult, very difficult. I'm not saying that it is impossible to debug such scenario, but would make it a mess. It would make it very difficult to handle, especially when some exception or interruption happen, right? So, and the difference between exception and interrupt is that, like, exception in this case where you have a program running, something goes wrong. Interrupt is the case when some part of the OS would interrupt, would want to, like, you have a machine, you have also operating system. You are running a process, this program, OS says that, oh, hey, like you go out, like some other program should run on this CPU. Like this scheduling happens, it's in the hand of operating system. But like when you are executing and violating the assumption, basically, if these things happen, then something is things will go wrong in a big way. Because when another program comes for execution, it will change the whole total state of the system. And if you want to retrieve back the first program, then things could go wrong. So I'm not going into the detail because like these require, like, there are so many stuff that are relevant to this, but the takeaway is that the why aspect, why we want to preserve this property, which is very important, is to ensure that we deliver the state of the execution precisely to the programmer, so they can debug the program in a nice way, in an easy way, right? So that's And there are obviously like some other reasons, right? You make the recovery a lot easier. You make you know, this scheduling when you want to restart the process and so on. And from the schematic perspective, you know that in this example, right, we assume that the execution of all instructions are the same, right? But in the case of, let me see. In the case of how to fix this, this is one way of fixing it. In basically using some magic that I'm not going to elaborate. This magic is actually very simple. Is that you somehow, again, this is the same old trick that we discussed in the microarchitecture. If we like could do some trick that we do not reveal to the programmer, we are fine. In this case, we make a hole between the execution and the write back stage by adding a buffer where we can write to, and the programmer doesn't know about this buffer. So this is a buffer that we can introduce at the microarchitecture. Here it's called Reorder Buffer, that we can write, like as long as like we execute the instruction, we can write the result whenever it's ready to this reorder buffer. And this reorder buffer actually makes sure that whenever the oldest instruction has its value in the buffer, then it can go to the it can be written to the register file, meaning that the programmer become aware of this change, become aware of this architectural change. So imagine that like it is again the same old trick of like adding something, some construct, some hardware pieces that at the microarchitecture, which the programmer doesn't know about it, right? So this reorder buffer is a sort of memory that is not part of the ISA. It's not part of the microarchitecture. It's not part of the ISA, basically. Programmer doesn't know, but it's part of the microarchitecture. And again, the same old trick was that we can do mess in the microarchitecture as long as you are not changing the architectural state, as long as you are not revealing these changes to the microarchitecture, we are fine. Okay, that's it. So I'm not going into the detail of this, but you got the idea how this thing happened. Like you see that these were beautifully aligned. So you make sure that first one is written first, and the second one second, third one third, and then things are beautifully aligned, as you see. So this reorder buffer actually enabled that. So making sure, and some basically we added some additional hardware to enable that. So I guess, and yes, some detail about implementation, how this thing would happen, and this would provide also some nice way of forwarding values if there is a dependency, because like here we assume that there is no dependency between the instruction, but if there is dependencies, because for example, say there is a dependency between like this guy and this third one, these are written here, like we do not need to wait like until we write to the architecture. These values could be forwarded to the third one if there is a dependency. Here we assume that there is no dependency between instruction, but if there is a dependency, these forwarding values can be facilitated through this from this reordering buffer to the functional units that they require them at execution. as long as we don't write to the register, right? And whenever this needs to be written to the register file, you can write it to the register file when you change the architecture. You need to change the architecture state. There are some detail, obviously, that how this can be implemented in a nice way, because we have memory structure, and there are certain implementation of this which vary in terms of performance. You don't need to know about this detail, but obviously if you are interested, you can read this paper or other relevant papers, or also to your textbook to find out more information. But that was, I guess, enough in terms of this flavor that I wanted to give you about this advanced topic about microarchitecture. So at least you have some idea about this. But that's it. Let's stop here. I would stay here for a few minutes. If you have any question, I'm happy to discuss. So that was really, I mean, is the last class that we have. Unfortunately, I wish we had more. It was my pleasure to actually be the instructor and getting to know you in this class. I wish basically all the best, not only for this class, but also other classes that you have, and also for your endeavor in learning more about all of this interesting stuff. And be in touch at any time. As I mentioned, there are many opportunities. If you are interested in doing research, encourage you to keep in touch, and let me know if I can be of any help now or in the future, at any time.
Thank you. I did have one question about the homework before I leave. And it was just the second problem question. It's the first statement of it. It's the add immediate, but the third argument is done, where done is also the jump to that after that start that part of the MIPS program. I think that might just be a typo, but I'm not sure.
Let me open the greater scope. So my memory is not good, so I need to look at it. So you're referring to what question, first or second?
Question 2, where it says add I, then you use the S0 register, the 0 register, and then done. That first part. I know add I normally it's add immediate to the register S, or add immediate to the 0 register to give us the value in S0, but we're adding done, which done is not an immediate value. Unless we're saying that it's equal to 5 from that comment, but the problem is we also have a section at the bottom of that for done, like a memory address to jump to.
That's very good. That's very good. So it's 5, right? Very good catch. I saved that in the question. Very good. Thanks.
I was thinking that was probably just 5, where you would just add 5 to it, and then after the while loop it jumps to done. That's what I was thinking, but I wanted to make sure.
Yes, very good catch. Very good catch. Thanks. Yeah, I corrected it in the question, in description of question 2.
Right, and we are considering just like a single cycle pipeline MIPS processor for this, right?
Correct.
And this is like, we aren't doing any branch prediction or anything. This is just a regular, each one takes X number of cycles, and we just look at the number of instructions that it takes.
Exactly.
Okay.
Precisely. Yes.
I wanted to make sure this wasn't anything crazy, because it makes more sense.
Yes.
The second part was for the CPI.
Yes.
Like the jump instruction will take less cycles and things
Correct.
like that, I know.
Correct. Yes.
So I'll have to go back and refigure out the numbers for those. Right, they're in those slides, and they're in the textbook.
Yes.
Okay, that's it. I wanted to make sure I was looking at that correctly.
Awesome. Yeah. Fantastic. Yeah, thanks for mentioning this. Yeah.
Okay, thank you. I saw that you changed it. Thank you so much for teaching the class. It was very informative. I know the final is next week on Thursday, correct?
Correct. Yeah, and
That's when it's due.
yes, when it's due, I plan to release the questions to you on Wednesday. So you have, 2 full days to work on this. And as I mentioned, I give you also late submission. So for those who cannot, free to submit on Friday as well. So this is like normal exam. It requires like maybe 1 or 2 hours of your time, right? So this would give you flexibility of whenever you have time to work.
Right.
Yeah.
And this would be would this be similar in quantity to the midterm?
Yeah, very similar to the style like
Okay.
on midterm and also on other assignments.
And one final question before I stop asking you questions.
No,
Will this be the same format as the midterm where it's a number of points, but you don't need all of them? Like, or will we have to do all the questions on the final?
honestly, I haven't designed it yet.
Okay, that's fine. If you haven't designed it, I understand. It's all good.
But I will try to add, some additional questions. So you could choose and decide, or like you could do all.
Right. Like I know the questions for drawing the stack were really weird on the midterm, so those are the ones I skipped.
Right.
And the recursion one threw me for a loop. I had to do some digging into the textbook to figure out how to do that one.
Right. No, if that was useful, I'll try to, to have more questions, so we could have the flexibility to choose. If that is helpful, yeah.
Okay, thank you.
Sure, thank you. Yeah, it was a pleasure being in this class, and yeah, talking.
And good luck with your research, by the way, as well.
Thanks a lot. Yeah. Yeah, and be in touch in the future. All of you, looking forward to hearing from you and all of you and your successes. And yeah, pleasure meeting you.
All right, have a great weekend.
You too. Thank you.
Thank you for teaching us this semester. And I just have a quick question in regards to, I hate to be shallow, but I have a question sorry about that. I have a question that in regards to you said on the syllabus that we would have 8 quizzes and you would drop 2, but we haven't had 8 quizzes. So are you dropping 2 or just dropping 1? I just wanted to, just a clarification.
That's a good question. Yeah, that was the plan, but like the first assignment took long, and we couldn't have much 8 actually assignment. I'll try my best, but let me first. I have a full picture. I designed the final, and we get things, and when we have the final grades, do the curving stuff, and then I will decide how to drop or how to deal with this. So obviously, I want all of you, to get the best grade. But let us first see the whole picture, and then we'll decide. So the aim is to increase your grade as much as possible, but obviously we want to make sure that like the relative ranking of student grades are in the right order.
Thank you. I was just wondering because I was just like, oh, the format of the syllabus was different than the format of the class. So I was confused for a second, but thank you.
Thank you.
Oh, and have a good weekend.
You too. Bye, everybody.